Well, here at the beginning of lesson 5.3, we're going to review adding and subtracting polynomials. And we know that we can do this vertically as well as horizontally. I'm going to review the vertical way to do it first, and then we'll look at the horizontal way of doing these problems. If you're going to do this adding on number one vertically, then you would write out your first polynomial there, and then underneath that, write those terms in that second polynomial under the terms that they are alike. So my y squared will go under the 2y squared minus y under the y's of the first, and then my constant under the constant from the first polynomial. And then we just add the like terms from here. It's just a way, adding them up vertically like this is just a way of keeping track of them. We're adding, so make sure you follow rules for addition, and you end up with this polynomial when you combine those two. Number two, same idea, except now we have a subtraction problem, so we have to remember that when we write that second polynomial out. So I'm going to rewrite the first. I'm going to put a subtraction sign in there to remind myself that I'm subtracting this entire polynomial from the top one. I'm going to line them up under like terms first. Okay, and then what we have to remember is that when we are combining combining polynomials, that second one is being subtracted from the first one. That means every single set of terms is being subtracted. So we have to change the sign on all of them. We're going to change the addition sign, or I'm sorry, the subtraction sign to an addition sign, and that's going to change the sign on every single term in that second polynomial, only in that second polynomial. Okay, the one that follows the subtraction sign over here. And then we just combine again, following our rules for addition. All right, and we end up with that polynomial when we combine. Now, we can do the same thing without rewriting these polynomials vertically on top of each other. We can do that like in number three. We can just change these signs. Right here you've got this different sign, and then we know that everything after that is going to change signs. So you can do it like that, and then mentally sort these two polynomials into like terms. So we have a 6m3 over here and a negative m3 on this side. So those two will add to give us 5m to the third. We don't have an m squared or just an m to the first degree term in the first polynomial, so those don't have anything to add with, so we just rewrite them with that sign change. Okay, and then we've got two constants, a negative 5. We're going to add to that a positive 2, and so when we combine those, we will get that polynomial. Again, you could have done this stacking them on top of each other, making sure those terms were lined up. If you were going to line them up vertically, then the best thing to do is leave some space in here for those two terms that are missing in that second polynomial, and put the constant out there, and then you can line these up where they would go if there were an m squared up here, but we don't have any, so you can hold that spot with a 0m squared if you like. Otherwise, I mean, you don't have to do that. Same thing here, there's no m to the first power. All right, so when you line them up like that, then again, you have to remember to go back in. You're subtracting the entire polynomial, so we change those signs. So essentially, you're doing exactly the same thing. It's just a matter of which way you're more comfortable with. Looking down at number 5, we have the same idea here, except now we have an addition sign, and so this is actually a lot easier to do. The terms, the polynomials are not ordered by degree, so you need to make sure that you are combining all of those. Is probably easier so you don't miss a term. Probably easier to reorder them. So if you reorder the first one and then reorder that second one. So I'm just ordering them based on their degree. I'm going from greatest degree on the exponent to least. And so now visually I can make sure I'm not missing any of the terms being combined together. I mean, you don't have to do this, but it would definitely be helpful, especially starting out. Now I can see I have a negative 3q cubed and a negative 8q cubed. I don't have a q squared in this first polynomial, so I'm going to come over here and rewrite it here, the one that's from the second polynomial. I have a 7q in the first polynomial and negative q in the second, so that'll give me 6q. I don't have a constant in the first, so I'm going to rewrite that constant that is there in the second one. So either way that you like to do it, just bearing in mind that you need to make sure somehow keeping track of that you have added all the terms in together and that you're not just skipping over terms that aren't represented in both polynomials. Now moving down to some multiplication, they ask us to multiply to find the product and in 9 and 10. And the concept here is going to be the same as you've been used to. When we have a monomial being multiplied by a binomial, then we just distribute. So this 2x cubed times 5x, we're going to multiply those coefficients together, the 2 and the 5, to get 10. We are multiplying the x cubed by that x, so the rules for exponents say when the base is the same, we can multiply them. We rewrite the base of x, add those exponents. 3 plus the 1 gives us an exponent of 4. So that's our new first term. And then we just have to remember to go back, and just like always, when we distribute over both of the terms. So 2x3 times a negative 1 gives us a negative 2x cubed. So same concept, we're just dealing with variables of higher order, greater exponents, so we really have to keep track of our exponent rules when we're doing this. Number 10, we have two binomials that we're going to multiply together. This is just FOIL. We're going to multiply the first, the outer, the inner, and the last, and then make sure we combine those two in the middle. Right? That should be a review right there. Number 13, now we have a binomial. So this is two terms multiplied by a trinomial. And again, you've done this. We haven't done it a whole lot, but you have done this. In this case, you have to keep track of how we multiply. So we're going to multiply the y, that first term, by all three terms here. Then we go back and distribute that negative 1 to all three terms again. All right, so it's a little bit, there are going to be more terms than we have when we FOIL. So I'm going to start with that y times that y squared. I'm going to rewrite the base, add the exponents, do the same thing with the y and that middle term to give me 6, the 6 and the 1 coefficient, multiply together, give me 6, rewrite the base, add the exponents, and then the y times that negative 2 constant. All right, I'm going to go back now and do the same thing with this negative 1. The great thing about that negative 1 is all it's doing is changing the signs on each of these terms in here. So not a whole lot of thinking that you need to do there. And then to be completed, we have to combine our like terms. We have a 6y squared and a negative 5y squared. I'm sorry, a 6y squared and a negative y squared that gives us a positive 5y squared. Combine those two y terms to give us negative 8y, and then I only have one constant. And so here we go. You've got those four terms that can't be combined in any other way. So that is simplest terms. All right, 15 and 16 are a review. 15, that is a square of a binomial. So that follows this pattern that we've been working with a lot lately. Okay. So if we identify A, we come over here, we see our A is X. And our B in this case is 3. So we can just plug those numbers into our formula over here. We'll end up with x squared minus 2 times a times b plus b squared. And so that would be 3 squared, like that. And then I'm just going to simplify it. Okay. And there's our answer for that one. Now, if you forgot, go blank and forget the pattern, then you could just rewrite x minus 3 times x minus 3, because that's what x minus 3 squared means, and then FOIL, and you'll get the same thing as we got here. Going down to number 16 then, we have the same idea, except now we are dealing with a square of binomial, but it's a sum in between. We have a addition sign. So same idea though. This follows this pattern now. We just put that plus sign in there instead of the subtraction sign. All right, then I go over here, I identify my a as 4t and my b as 1. So I'm going to plug those in over here. 4t squared plus 1 squared. Remember to square both the coefficient and the t squared. All right, and so here is the answer there. Once again, though, if your mind went blank and you aren't able to pull the pattern out to use it, then you can rewrite 4t plus 4t twice, because that's what 4t plus 1 squared means, and then FOIL. Combine the like terms and you'll get the same answer. Now, number 17, the cube of a binomial actually has a pattern as well. Just like 15 and 16 follow a square binomial pattern, the cubed binomials also have a pattern that they follow. It's a little more challenging to memorize, but it looks like this. So a minus b cubed. Once you've identified your a and your b, then it's going to follow this pattern right here. Okay, so more terms, more exponents, more things kind of going on in here to memorize. But this is how it works, just the same as 15 and 16. If we identify our a here as z and our b as -5, and then we're going to, I'm sorry, not -5, 5. Then we will go in to the pattern and plug those numbers in. So we'll end up with z cubed minus 3 times z squared times this 5 that we have identified as b. All right, so basically everywhere we see an a, I've plugged in z, and everywhere we see a b in the formula, I've plugged in 5. And then from there, do the algebra on it to simplify it. And we end up with this as our final answer. If that pattern isn't memorized, then what you would need to do is rewrite z minus 5 3 times. You would FOIL the first two and you would get a binomial. And then you would FOIL that new binomial with this one over here. Right? We've done things similar to this in the past. Usually it's 2 binomials and a monomial that has to be distributed then after we've FOILed here. But this works the same way. You would just FOIL 2 of them and then take that new binomial with them combined and FOIL with the third one. In 19, we're going to use the volume the formula for a volume of a rectangular prism to figure out the volume of this polynomial. So we're not actually going to be getting a number, a whole number for this. We're just getting a polynomial that we're going to write in standard form so that we could figure out the volume of this figure if we had a value for x for it. So we're going to use this formula here. We know that we can identify this as the length, this right here is the width, and this as the height. Okay, so we're just going to take those expressions and we're going to plug them into our formula. Volume equals length times width times the height. So the length in this case is represented by the expression x plus 6. The width is x, and I'm going to put that in parentheses, and then the height is 2x plus 1. I'm going to reorder these a little bit. You can multiply them in any order you want. I'm going to put these two binomials together first so that I can FOIL right here. So I'm going to FOIL here between these two. And I'm not going to forget about this x out there. I'm going to put that out here in parentheses. I'm going to combine my like terms. Actually, I made a mistake right here. When I did my last terms, that should be a positive 6. All right, and all of this is going to be multiplied by this x. That was the width. So now all I'm doing is, that's just a monomial. I'm just going to distribute that to each term. All right, and so this ends up being in standard form. So we know it's in standard form because the exponents are going down in decreasing order. This is the volume of the figure written as a polynomial in standard form. All right, and in number 21, we have a word problem that's bringing in this idea of multiplying polynomials. They've given us two functions. The first one models the per person consumption of bottled water in gallons per year. And then the second function is the population of the United States per year. And T is representing those years since 1990. They want us to write a model for the total consumption, the total amount of bottled water that is consumed in the United States. All right, and then the last question after we've done that says what was the total consumption of bottled water in 1998. So that's the second part. We've got to write the model first, and the way we do this is to multiply these two polynomials together. This is the number models the consumption of bottled water per person, and this tells us the model of how many people were in the United States. So if we multiply the two together, we can get an idea. We can get another model that represents bottles consumed in any individual year that we would want to plug in. So we will rewrite the two of these. I'm starting with that bottom one for no particular reason. I'm going to write that first, and I'm going to multiply that by the three terms in the function for number of bottles consumed. All right, so each one, the decimals, the large number for the constants and the coefficients, and then we have decimals for coefficients over here. It gives the whole thing a much more complicated look to it than it really is. If you really take a minute to look this over, all you're looking at here are, this right here is a coefficient on a t. This is a t to the first degree, all right? And this right here is the constant. So if you really step back and look at this model over here, it's a linear equation of the form y equals mx plus b. It's just that we have a slope that's quite large, and we have a y-intercept that's quite large. But otherwise, it's just a normal linear equation, okay? It's just a binomial. In this one over here, we have a trinomial. I mean, our highest order is t squared. And then we have a t to the first degree, and then we have a constant. So here we have a quadratic, here we have a linear equation, and they're just have strange coefficients, ones that we're not quite used to. But we're going to do this the same way that we have always done it. We're just going to multiply the binomial by that trinomial. And we'll do that by taking this first term here and multiplying by the first term in that second equation. So when I do that, and I'm going to want a calculator for that, I'm going to take those two coefficients, multiply them together, and I get that for my new coefficient, rewrite the t base, because we're going to multiply those now, and add those coefficients. I'm going to do the same thing with this first term and the middle term over there. And when I plug those two coefficients into my calculator, I get this here. I have a t and a t over here. I'm going to rewrite the base, add the exponents to get a t squared. I'll do the same thing again, just now with that last term. The last term is a constant, so I don't have any variables to combine, but I get a coefficient of this right here, and then can't forget about that t in my first term. So that's what I get after I multiply the first term by these three. I'll go back and do the second one. I'm going to come down here on this line here just to, because I'm running out of room. So I'm 250,359 times this first term here. When I plug that into my calculator, I get this right here. All right, this is a constant, so I don't have anything to multiply by this variable t squared over here, so I'm just going to keep the t squared, stays the same. All right, same thing with the next one. All right, this is what I get when I multiply 250,359 times 0.186, that coefficient. And then I'm just going to keep that t. I don't have any t's over here to multiply with. And then when I multiply these two constants together, I get this large number here. All right, so you can see from there, I'm going to need to combine all the like terms in order to simplify it. And so when I do that, I get C of t, so the consumption based on the year t. That's how I want to write that. This will be my lead term. My second term. Third term, and then that last constant. All right, that last question asks, what is the total consumption of bottled water in 1998? Well, if we go back up there to the beginning of that, it says where t is the number of years since 1990. So we're going to fill in 1998 minus 1990 gives me 8 years since 1990. So I'm going to come into the function. I'm going to evaluate at t of 8. Remember, this is just for information purposes only. You're not multiplying c and a together. It's just saying we're going to find c. We're going to find the value of the function when t is 8. So then I would come in here. I'm not going to rewrite all of this, but I would drop the 8 in every time I saw a t. And then I have to go back to the calculator and recalculate all that out again for a final answer of, when I do all that, this was what will come up in my calculator, and that is in thousands of gallons. That's the label.